Hey guys, it's Miss Rainey. I hope you are staying warm on this cold winter's day. I wanted to brighten up your day and warm it up a little bit with some chemistry. Today we're going to learn a little bit about mole fraction and Beer's law and do some calculations on both of them. So get out your calculators and your periodic tables and let's get started. Okay, mole fraction is our first thing that we're going to talk about today. So mole fraction is a fraction that's based on moles. That kind of seems obvious, right? And so it's just like a percentage, except that it's missing the times 100 at the end. So it does not have that. But it does have everything else that a fraction has, which is the moles of part divided by the total. So it's just a part over a whole, just like a percentage is. It's just missing the times 100 to get it into a percentage. And then also it's part moles, the moles of the part and the moles of the whole. That's why it's called the mole fraction. So for example, if you have a mole fraction of 0.10, that's the same thing as saying 10% of the moles of one part of one component is the solution. So if your sugar solution was a mole fraction of 0.10, that would mean 10% of the moles were sugar and 90% of the moles in the total solution are probably water. It's probably an aqueous solution, something along those lines. So let's look at a calculation involving mole fraction. So we're going to find the mole fraction of sugar in an aqueous solution, 30 grams of sugar and 70 grams of water. So what we have to do is find the moles of each of these things. So we're going to take that 30 grams sugar and that 70 grams water and turn both of those things into moles. Okay, notice that it says the molar mass of sugar is 342 g-mol -1. This is the College Board's fancy way of saying grams per mole. That's the way that they're going to write it, so just kind of get used to that. Which means that when you're doing that factor label, when you change grams to moles, you'll say 1 mole is 342 grams. Quick calculation tells me that 0.0877 moles of sugar are in this solution. For the water, we're going to do the exact same thing. We're going to change the grams into moles. And for water, the grams is 18 because it's H2O, which is 2 plus 16. So quick calculation says 70 divided by 18. And 3.889 moles. So now I know how many moles of sugar that I have and how many moles of water that I have. So to get my mole fraction, which is part over whole, I need the whole. So I'm going to add those two together. So the 0.388 plus 0.0877 is 3.977 moles total. So then mole fraction is going to be the part over the whole. So that'll be 0.0877. I'm going to move it up here so I have some space. Divided by 3.977. So type that in real fast. And it looks like 0.022. So 0.022 is my mole fraction. There is no unit on mole fraction because it would have been moles divided by moles, so the unit cancels out. That's equivalent to about 2.2% of sugar. So the next question says, find the mole fraction of water in the sugar solution above. So we want to do the exact same thing. So we had that 30 grams of sugar, and that was equal to 0.0877 moles. And we had that 70 grams of water, and that was equal to 3.889 moles. And then we added those together, and I get 3.976 moles. So far I'm doing exactly the same thing I did before, except that now that I want the mole fraction with the water, I'm going to take the moles of water divided by the total instead of sugar divided by the total. So I'll take that divided by 3.889 divided by 3.976. Let's see. And I get 0.978, which is approximately 97.8% of the solution. And that answer makes sense because we said a minute ago that there was 2.2% sugar. And so then having 97.8% water really does kind of make sense. The reason why mole fraction might be useful is if you're looking for the total number of particles, total number of molecules in a solution, rather than looking for the total volume of the solution or the total mass of a solution, like you would be doing for molarity or molality. All right, let's move on. Now we've got Beer's law, also known as the Beer-Lambert law, depending on which one of the scientists you want to give credit to. Okay, so Beer's law is A equals ABC, which seems like a really simple kind of formula. It says that if a solution absorbs visible light, in other words, a solution is colored, the amount of absorbing particles is directly related to the number of moles of solute in the solution, which is measured by molar concentration. So an increased concentration relates to an increased absorbance. Beer's law is used in quantitative analysis to determine the concentration of an unknown sample from absorbance data. So essentially what that says is if you have 2 cups of red Kool-Aid, and one of them is really dark red, and the other cup of Kool-Aid is kind of watery looking, and it's red, but it's not very dark red, then we can say that this one is probably more concentrated because it has a greater amount of solute in it. More concentrated. It has a greater amount of solute in it, therefore it absorbs more light, less light can get through. And so we can say the one that's a lighter color is less concentrated. So all we're saying here is the darker solution is more concentrated than the lighter solution, and based on how much light it absorbs, we can actually measure the concentration of the solution. So let's calculate a little bit with this. The first thing we're going to need to know for our calculation is what all these letters mean in this formula. So my first capital A is the absorbance. It's related to the amount of light absorbed by the solution. So this number is higher when there's more light absorbed or lower when there's less light absorbed. When light is absorbed. And so then the little a, I'm sorry, they're confusing, is the molar absorptivity. It's a proportionality constant, and the slope of a Beer's law plot. Sorry, that word stuck in my throat. Okay, constant. This is what's important here. This number won't change for a particular solution at a particular concentration, so we just need to know that that's a constant number. Also, the unit for this number is kind of weird. It's 1 divided by molarity divided by centimeters, otherwise known as molarity -1, centimeters -1. Then we have B, that's the path length of the radiation through the absorbing medium in centimeters. So this is usually like we've got a square test tube, a cuvette, and the light's going to go from one side through the other, and so it's going to absorb. Well, this one's the length, the distance between how far the light has to travel through the solution. And so usually most of our cuvettes are 1 centimeter long, or 1 centimeter wide. So if you're not given any other information, just assume that your path length is 1 centimeter. And then finally we have C, which is concentration, and so then this is just the molarity of a solution. All right, let's look at an actual problem with this. This one's not in your notes, I just made it up off the top of my head just a minute ago. It says, what is the extinction coefficient, the molar absorptivity constant, that's this little a, of a 0.35 molar solution that has an absorption of 0.75. So also notice that there is no unit on the absorption. I don't know why, it's a little bit more complicated than what we need to know anyway. So we have 0.75 is equal to, not sure, times path length, When it doesn't tell you, assume your path length is 1 centimeter, and then your concentration is 0.35 molar. So we'll take 0.75 divided by 0.35 divided by 1, and we get x to be equal to 2.14. Since we divided by centimeters and we divided by molarity, the unit is molarity -1, centimeters -1. All right, last but not least, we're going to look at a plot. This is actually what you're going to be doing with a lab on Beer's Law, is making a plot of absorbance versus concentration. And you'll notice that as the absorbance increases, the concentration increases, so you get a direct relationship. So, the absorbance of an unknown solution is 0.45, which should be somewhere around here. What is the concentration of the solution? So this plot looks really nice and straight. I could probably draw a straight line over and probably draw a straight line down and probably get a pretty good number just based on my graph. But it seems like, what if my numbers weren't so nice and so even? So maybe I can look at an actual calculation. So I could say, for example, at 0.8, the concentration is 0.4. So if the concentration is 0.4 when the absorbance is 0.8, what will the concentration be when the absorbance is 0.45? I'm just going to set a direct proportion. So I'll say 0.4 times 0.45 divided by 0.8 gives me 0.225. And the concentration's in units of molarity, and that's all there is to it. I randomly picked 0.8, but you could have also, say, picked 0.2 and 0.1, just really anything that fits along that line. Or you could have actually used the slope. Find the slope of the line, which is equal, sorry about my handwriting, guys, to little a. That's equal to the absorptivity constant, and then you can use that little a in this formula to solve for concentration. That's what you're going to do in an actual lab scenario, because in an actual lab scenario your graph is going to look more like kind of one of those guys. So it's not going to be straight, so you can't just pick any random point off the line. You want the slope, which will give you a straight best fit line. Okay, that was Molefaction and Beer's Law. Stay warm, guys. See you later.